Okay, this morning I want to show you how to derive performance equations, or we call it design equation, for another flow reactor that is plug flow reactor, or we simply call it PFR. So design equation for flow reactors is depending on the same theories that the more the time spent in the reactor, it increases when we increase the reactor volume. So this is referring to the reactants of the reaction itself. So the reactant will spend more time if we increase the reactor volume. Or we could say that the bigger or the longer the reactor, the more time it will take for the reactants to flow completely through the reactor, and thus the more time to react. So if we have Fa naught is equals to molar flow rate of A, therefore the molar rate at which species A reacting within the entire volume or within the entire system is written as Fa naught X. So it is also equals to Fa naught is X is when the mole of A fat, the number of mole of A fat over time with mole of A reacted per mole of A fat. So finally we have Fa naught equals to mole of A reacted over time. So it's actually describing how many moles of A have reacted per time. So the unit is basically unit of mole over unit of time. So it could be mole per hour, mole per minute, or mole per second. So let's start here. The molar flow rate of A that leaves the system is when the molar flow rate of A that we initially fed into the reactor minus the molar flow rate of A consumed. So we can write this equation as Fa equals to Fa naught minus Fa naught X. Should be minus there. So Fa equals to Fa naught minus Fa naught X. So how to get the Fa naught's value is the entering molar flow rate. Fa naught is actually the entering molar flow rate of species A, or we could say here this is the reactant, but the unit will be in mole per second, mole per minute, or mole per hour. And we calculate Fa naught from Ca naught and V naught. So in this case, Ca naught is the entering concentration of reactants A. The unit will be in mole per unit of volume, mole per decimeter cube, mole per meter cube, and so on. Mole per liter, also mole per liter. And V naught is the entering volumetric flow rate. The unit will be in volume per unit of time. So this is for fluids, where the Ca naught is commonly given in terms of molarity. For gases, the value of initial concentration Ca naught is calculated using the gas law, where Ca naught equals to Y A naught P naught over R T naught. Where in this case, Y A naught is the mole fraction of A, P naught is the initial pressure, R is the gas constant, and T naught is the initial temperature. Okay, we start with general mole balance equations, where we have everything that goes into the system minus everything goes out from the system, plus generation will be equals to accumulations. So the in is actually FA naught minus FA plus integration of RAdV will be equals to dNA over dt. So PFR derivation started with general Molecular system volume V. As we can say in the image that the PFR is some kind of reactor that is designed in pipe in shape. So we don't have any stirring devices where the mixing is expected to be occur, or depending on how the reactants and the product is flowing from one end to the other end of the reactors. So we have in minus out plus generation will be equals to accumulation. We have FA naught minus FA plus integrations of RAdV will be equals to dNA over dt. As we know that when we do the analysis during the reactions, we assuming the analysis was done during the system under steady state. That means the accumulation term will be 0, which is dNA over dt will be equals to 0. Therefore, we have FA naught minus FA plus integrations of RAdV equals to 0. And in this case, as I said earlier, we don't have any stirring or mixing devices inside the piping system, so the generation term will stay as it is. From here, we differentiate the term with respect to volume. So we have d, the whole term, over dv. Since FA naught is constant value, which means that we know the molar flow rate that goes into the system from earlier or at the beginning of the reactions, so FA naught will turn into 0. So differentiate FA will give dFA over dV, and differentiate integration term will somehow cancel it out, so we have RA. So finally we have minus dFA over dV will be equals to minus RA. We rearrange it, so we cancel the minus signs from both sides. We have dFA over dV equals to RA. So since from the previous slide we have design equations in terms of conversion is dFA over dV equals to RA. So if we want to write the design equation of blood flow reactor in terms of conversion, we need to take up from definition of conversion for a flow system, where we have FA equals to FA naught minus FA naught X. What we do is we differentiate this definition of FA will give us FA dFA. FA naught is 0 because FA naught is a constant value. Differentiate constant value will give us 0, and differentiate FA naught X will give us FA naught dx. So we replace this, substitute this dFA term into performance equation, will give us negative FA naught dx over dV equals to RA. So basically, replace dFA here with dFA here, so the whole term here will be goes to here, and that's why we have negative FA naught dx over dV equals to RA. So finally, we have this design equation of PFR in terms of conversion. We arrange the minus signs, so we have F A naught dx over dv equals to minus RA. So we arrange this. Okay, so we have F A naught dx over RA equals to dv. So as I said earlier, we are looking for the volume of the PFR. As we increase the reactor volume, we allow reactants to stay longer in the reactor, and then we are expecting more conversion out of it. So to calculate or to evaluate the PFR volumes, we need to do the integrations of dV, integration both sides dV, and integrate dx over RA. So we have here the performance equations. V equals to FA naught integrate dx over negative RA. So basically, we don't take out the RA from the integration term because RA has the conversion term inside it, which require us to do the integration. So we need to put RA inside the integration terms. So this is an example from the past questions, March 2015, question 3. A. The question statement given is at 650 degrees Celsius and 460 kilopascal, phosphine decomposes homogeneously with a rate constant of 16 per hour. Given R gas constant equals to 8.314 joule per mole Kelvin. The reaction scheme given is actually showing gas phase reaction where we have 4 mole of phosphine decomposed into P4 and hydrogen gas. So it doesn't say anything about elementary, but from the rate constant unit that shows the reaction is actually first order. The question asking us to calculate the volume of plug flow reactor which can produce 80% of conversion for the feed, where the feed consisting of 40 mole per hour of pure phosphine. Okay, so there are a few informations there. We know this is a gas constant, so as I showed you before, the concentration of gas can be calculated from ideal gas equation. In this case, we have initial pressure, initial temperature, and the mole fraction is only 1, which is on one gas only. Okay, so from the statement, we know that the FA naught given is 40 mole per hour, so that is FA naught. Reaction is first order based on the rate constant, unit for rate constant, and means that the rate law negative R equals to KCA, okay, or we can write as K CA naught 1 minus X. And the design equation as we derived previously for PFR equals to FA naught integrates dx over negative RA. So we insert everything here. Into this equation, okay, so what should be done here is we need to solve the design equation just now, where we have V equals to FA naught integrations of dx over minus RA, and FA naught integrations of dx over minus RA is KCA naught 1 minus x. Since the K and CA naught is actually constant value, so we take out everything from the integration term. So we have K CA naught here. What leaves us is dx over minus 1 minus x. So we just integrate 1 minus x. So finally you have FA naught over K CA naught, okay, ln of, integrate 1 over minus x, give us 1 over 1 minus x, ln of, within the limit that is x equals to 0.8 and x equals to 0. So here is the reference where we integrate dx over 1 minus x equals to ln of 1 over 1 minus x. So to evaluate the volume, so we need to insert all the values, mole per hour, the concentrations value that you need to calculate. The K is 16 per hour, and a ln of 1 over 1 minus 0.8 minus ln of 1 over 1 minus 0. Okay, when you solve this, you will get the volume in terms of, if I'm not mistaken, meter cube. Alright.